All right, get your face out of the way. All right, so for the second half of 11.4, we're going to talk a little bit more about the two-way tables we did in the first half, and then bring some tree diagrams in that are really helpful in showing conditional probability. So let's get right to it. Our EQ is how can I use tree diagrams to display conditional probabilities. Um, this is an ACT type question that we're going to start off with as a quick little review. Again, just like standardized multiple choice math test question. It says sales per business were $3 million more the second year than the first. And then sales for the third year were double the sales for the second year. Okay. And then we have if sales for the third year were $38 million, what were sales in millions of dollars for the first year? Okay. With all of these multiple choice questions, lots of different ways you could answer it. What I'm going to do here is I'm going to kind of set up a little table. Year one, year two, year three. And I know year three is $38 million. That first underlined statement I have says $3 million more the second year than the first, which means the transition from year one to year two is plus three, right? $3 million more in year two than year one. And then the second underlined statement says sales for the third year were double sales for the second year. So to go from year two to year three, sales doubled. Okay, so now it's really just working backwards. Well, if year three, I'm told that there was $38 million in sales, what number times 2 would lead me to that 38 million? So I can guess and check, or I can just use division. I can go 38 divided by 2, and I'll get 19. So that checks out. 19 times 2, 19 million times 2 gives me 38 million. So I know year 2 is 19. Okay. But then it's asking for what was it in year one? Well, what number plus 3 million would give me 19, and that's going to be 16. So we can come over here and see that $16 million is the sales for year one. So one thing I want to talk about is what happens if like a table like this doesn't have all the information given. It's not Sudoku, but the idea that if you're familiar with Sudoku, this is a similar-ish concept where there's enough information that you can figure out the rest. So this data or this table has people split up into right or left-handed, and were you born before 2002 or after 2002? Okay. So right away, I see that I have 30 righties and 6 lefties for the born before 02 category. But remember, we kind of had what we decided in the last video is that if I can put some totals on here, this is going to be really helpful. So 30 plus 6 that means there were 36 people surveyed that were born before 2002. I can then go down the right-handed column, right down that first column, and see 30 people were born before 02, 42 people were born after 02, so that gives me a total of 72 there. I can go down this way. If I know 6 lefties and there are 21 total lefties. And again, it's important to remember this is the total. So if this is 6, that other number has to add up to 21. So 15 goes there. Now I can move straight across. So you see how like the pieces kind of fall into place. 42 and 15 makes 57. Now, to know I did this right, or one of the ways to know you did it right, is when I add the totals up, when I add these two together, that should be the same as when I add those two together. And whatever number I get goes in the lower right. I don't add all 4 of them up. So to check this, 72 plus 21, that says there are 93 people total in this survey. If I do 36 plus 57, I also have 93. So that's the number of people that were surveyed overall. So there I've finished my table, and now I can answer these questions. What's the probability that I pick someone who's left-handed? There's no given probability here. There's no that vertical line, which means I'm picking from all 93 people. What's the probability they are left-handed? Well, here's my left-handed column. Which of those three numbers am I going to use? Since I'm not using a given probability, I'm just going to use 21. So 21 out of 93. Again, you could probably just leave it as a fraction, but as a decimal, it's 0.226. Okay. What's the probability that the person was born after 2002? Again, no given information, so my sample space is going to stay at 93. How many people were born after 02? It's all here, so it's 57. So 57 out of 93. Yeah, in tests, you're going to see both 0.613. Sometimes you'll see two decimals, sometimes three, sometimes fractions, sometimes not. And so just understanding that there's multiple ways to read probabilities is pretty important. Now, here's our first given. What is the probability that you choose someone who is left-handed given they were born after 02? So if I look at the people who were born after 02, that means I am only working with these 57 people. So out of 57, oh boy. So my sample space is going to be out of 57. What is the probability that they are lefty? Well, of my highlighted portion, those are my lefties. So 15 is going to be my event space. 15 out of 57 is 28%. Yes. 0.263. Okay. And then finally, what happens if we flip it now? Okay. So instead of the given event being they were born after 02, now the given event is they are left-handed, which means I'm going to switch my highlighted region. This now is my set of people I'm working with. So out of 21, how many of them were born after 02? And it's 15. So 15 out of 21, which is 0.714. Okay. So if the table's not complete, you can make that total column and kind of figure out the missing information. Okay. Tree diagrams are the last thing we have to talk about in this section, and they're super, super helpful when you want to talk conditional probabilities. So let's say, suppose among all ROS students, 20% own a car. Okay. Of everyone at ROS, 20% own a car. So what I'm going to do is at the beginning of this tree, I'm going to put, who am I talking about? Well, I'm talking about ROS students. Okay. And then the first statement in this problem splits the ROS students into two groups. It splits them into people that own a car and people that don't own a car. Okay. So what I'm doing now is of ROS students, I'm splitting them into two groups. They own a car or they don't own a car. Okay, so everyone at ROS is split into one of these two categories. And the statement says 20% own a car. So what I'm going to do is I'm going to go ahead and just put that probability right here. So 0.20 or 20% of people own a car. And then by default, everyone fits into one of the two categories. So that means the remaining people, or 80%, do not own a car. Okay. So if you're a student at ROS, 20% own a car, 80% don't. And then this next statement is actually a given probability without saying it. Of those that own a car, okay, so if we just look at the people who own a car, 70% are seniors. Okay, so right now we are only talking about this group of people right here, those that own a car. We're going to take that group of people and split them into two different categories. We're going to split them into seniors. We're going to split them into non-seniors. Okay, so of the people that own a car, 70% are seniors. So this is 0.70. and then the non-seniors would be 0.30. Okay. Now, what's crazy is that those numbers, the 0.70 and the 0.30, are actually given probabilities. Okay. This is if I know they own a car, then you have a 70% chance of being a senior and a 30% chance of being a non-senior. Okay. The next statement here says only 10% of those who don't own a car are seniors. So of all the people who don't own a car, they are also split into seniors and non-seniors. But because there are so many freshmen, sophomores, juniors that don't have their license, the people who don't own a car, that's why it's such a small number of seniors. So only 10% of the non-car owners are seniors because there's such an overwhelming number of sophomores and juniors, or freshmen, sophomores, and juniors that don't own a car. Okay. So what we've done is we've split these students up into, or we've split all the students at Roz into basically 4 different categories: seniors with a car, non-seniors with a car, seniors without a car, and non-seniors without a car. Okay. So what's happening with this tree diagram is all of these right here are given probabilities. Okay. These are given. So if I said, what's the probability that you pick a non-senior given they own a car? Well, if it's given they own a car, that puts me right here. What's the probability they're not a senior? 0.30. Okay. And so you might be asking yourself, well, then what's the point of the 0.20 and the 0.80 at the beginning of the problem? Okay. And what we need to do is those numbers are going to help us to find the and probabilities. Meaning, if I asked you, what's the probability that you pick a senior and they own a car? Okay. So senior with a car. I would have to then multiply the numbers that follow the branches that lead to that end. Okay. So 20% own a car. Of those people, 70% are seniors. So I'm going to multiply 0.20 and 0.70 to give me what percentage of everyone would be a senior that owns a car. So 0.2 times 0.7 is 0.14, meaning 14%. I'm going to get this out of here. So 14% are seniors with a car. Okay. So I can do the same thing for the next step. How many of everyone, how many people own a car and are not seniors? Well, I'm going to take 0.20 times 0.30, and that gives me 0.06. Okay. So, and this is getting a little involved, this next statement, but 0.14 and 0.06, those two numbers should add up to 20%. So everyone who owns a car is 20% of the student body. And then that 20% is made up of 14% of the students are seniors, and then 6% own a car and are not seniors. Okay. If I do the same thing here, 0.80 times 0.1, that gives me 8% of the entire student body is a senior without a car. And then that leaves a massive number of 0.72, which is 72% of the student body doesn't have a car and they're not a senior. Okay. So these here, purple doesn't work real well. These are what we call the and probabilities. Okay. So if you're asked a question about what's the probability you choose someone who's a senior and has a car, that's where we're going to use the end of the branches of the tree diagram. Okay. So this is something you're definitely going to have to practice with because it is a lot of interpreting the information, but it also helps us to break down the sets of people very quickly based on only two or three sentences of information. Okay. So then the question actually asks, I didn't even answer the question. Using the tree diagram, what percent of RAs are seniors? What percent of all of RAs are seniors? Okay. And if I look at the end here in my blue box, there's actually two groups of people that would be considered seniors, right? There's the seniors with a car and there are the seniors without a car. So if I want to know what's the probability what percent of RAs are seniors, I'm going to take those two different categories and add them up. I have the seniors with the car and the seniors without. Okay, and so that is 0.14 plus 0.08, which is 0.22 or 22%. So 22% of the students at RAS are seniors, which makes sense because it should be pretty close to 25 because we've got 4 different grade levels at the school. So lots of stuff going on. Okay, we're going to look at one more tree diagram example, and then we'll wrap this one up. All right. So there's a survey of all incarcerated adults, meaning those that are imprisoned. Okay. So the first statement here is of the U.S. population, 0.91% are currently incarcerated, meaning they're in prison. Okay. So if we start this tree diagram, we have the entire U.S. population is who we're starting with. Okay. And then I'm taking the entire population of the U.S. and splitting into two categories. Those are in prison, and we have those that are not in prison. Okay. Now, it says 0.91% are currently in prison of everybody. Now, you got to be a little careful with that because 0.91% does not mean 0.91. I have to take my percentage and divide by 100 or move the decimal a couple times. So the decimal probability that I choose someone at random that's in prison is 0.0091. Okay. Everyone else would have to not be in prison because there's only two different categories there. So what I'm going to do is I'm going to take 1, which represents 100%, and subtract those that are in prison. And that gives me the decimal for those that are not in prison. So over 99% of people are not in prison, but then just under 1% of people are in prison. Okay, so that's my first split as far as the this problem that I'm given. The next statement says, of those in prison, 30% have not attained their high school diploma. Okay, so then from prison, I'm going to split these into two categories. Those with the high school diploma and those without high school diploma. Okay, and it says 30% have not attained their high school diploma. So this is 0.30. So then that means 70% have attained their high school diploma. Okay, and then finally, my last statement that I'm given is of those not in prison, 86% have attained their high school diploma. So I'm going to do the same split for the people that aren't in prison. Okay, high school diploma. I'll move this down. So high school diploma is 86%. And then the people that don't have their high school diploma is going to be the rest, which 86%, that's 14% away. Again, you could 1 minus 0.86 to get 0.14. Okay, oops, don't want to graph it. So this is our tree diagram. And then based on what we're being asked, we could answer questions based off of this. Again, if you wanted to find the probability that someone is in prison and has their high school diploma, I would take the probability they're in prison times the probability that they have their high school diploma if they are in prison. And that would give me the probability of picking someone at random in the entire US that is in prison with their high school degree. Okay, so that's the setup of our tree diagram, and then we can answer questions off of it. So let's try a couple of these real quick. This is just a replica of what we just made. What is the probability of randomly selecting someone from the US who is not in prison and has a high school diploma? And this word "and" is super important. That means I'm going to have to multiply. Okay, they are not in prison and they have their high school diploma. So I'm going to take 0.9909 and times that by 0.86. So the probability I choose someone is 0.852, or about 85.2%. Okay, what is the probability? The next question we're going to, what is the probability randomly selecting someone with a high school diploma? Okay, there's no "and", there's no word "and", and there's no word "given". So that means I want everyone that has a high school diploma together. Okay, and that there's two sets of categories here. There's the people who aren't in prison that have their diploma, but we can't forget the people who are in prison that still have their diploma. Okay, and this number we already figured out from the previous problem is 0.852. We just have to figure out what percent of the entire US is in prison with a high school diploma. So we'll do 0.0091 times 0.7, and that's 0.006. Okay, so then to answer the second question, I'm going to add those up, and then 0.006 plus 0.852, a little bit of rounding going on here, is 0.858. And then the follow-up question, and what we would discuss if we were in class, and maybe we'll have an online discussion, is why are those two numbers so similar? Why is the probability of someone being not in prison with a high school diploma so close to just the probability that you pick someone that has their high school diploma? So I'm not going to answer that because there's lots of different ways to interpret this information, and it's pretty heavy stuff. So we'll leave that alone for now, and hopefully we can get to it either in the building or online. But to summarize, how can I use tree diagrams to display conditional probabilities? We're going to use the tree to split into two categories. Use the tree to split the sample space into, well, I'll say into groups. So this is trait number 1. And then from here, we have 2 additional splits that has trait number 2. Okay. So just want to kind of, these are going to be, on that part of the tree, you're going to have some basic probabilities. In this part of the tree, you're going to have given probabilities. And finally, at the end of the tree, if you use multiplication, you will have, let's pick green right here. These will be your quote unquote "and" probabilities. Probabilities. And then I'm just going to make a little note that we need to multiply to get these. These will most likely not be given in the problem. Okay, so there's our summary for that lesson. Hopefully it wasn't too lengthy and those trees are kind of starting to make sense a little.